All right, everyone get ready, because today we're going deep into the world of energy,
Oh, yeah.
but specifically
Okay.
how we teach this really important concept.
Interesting.
You might think energy, like how hard can that be?
Right.
But it's surprising
Yeah.
how often even scientists get tripped up on the terms.
Yeah. I can imagine that.
Today we're really looking at
Okay.
why that energy stores and transfers approach
Mm-hmm.
is making such a splash
Yeah.
compared to that old energy forms and conversions.
Yeah. The classic. It's so fascinating how how fundamental it is,
Uh-huh.
but we still don't have a simple agreed upon definition.
Right.
Notice is like defining time.
Exactly.
We know it exists. We see what it does.
We experience it.
Yeah, we experience it, but
But how do you explain it?
yeah, putting it into words is so slippery.
Totally.
It really is.
So we've got these excerpts
Okay.
from the 2024 Singapore-Cambridge General Certificate of Education, Ordinary Level Physics Syllabus.
Wow, that's a mouthful.
It is a mouthful, but they use this energy stores and transfer method a lot.
Oh.
And we also have this research paper from the BEST project.
Best project.
And BEST stands for?
Building expertise in science teaching.
Exactly. They dove deep into how students learn about energy
Ah, very cool.
and what they find.
Well, they found that kids often think about energy like it's this internal fuel tank.
Oh, interesting.
I'm full of energy. I can run around.
Right.
It makes sense. It's relatable, but obviously not the whole picture scientifically.
Yeah.
Yeah.
Like,
yeah.
I'm running low on coffee is like my personal energy crisis.
Right.
But that's not really how thermodynamics works.
Yeah.
Not quite.
Not quite.
That's where it gets kind of tricky.
Yeah.
Both of our sources
Okay.
talk about this really big misconception
Okay.
that energy is like a thing, like a fuel that gets used up.
Oh, yeah. I see that a lot.
Yeah.
And it's reinforced everywhere.
Right.
We say things like energy consumption. That
Oh.
makes it sound like the energy just vanishes.
Poof.
Gone.
Okay.
So no wonder
Yeah.
even students who've had a formal instruction about it
Right.
still struggle
With the concept.
to grasp energy conservation. They're trying to fit a square peg in a round hole conceptually.
Totally. And so how does this
Yeah.
energy stores and transfers approach actually work?
So instead of thinking about energy
Okay.
as this blob
Mhm.
that morphs from one form to another,
Yeah.
we think of it as being held in different stores.
Okay, like different container
It's like containers
just
for
energy.
Yeah, so you've got kinetic energy, the energy of motion,
Mm-hmm.
potential energy, energy due to position,
Okay.
thermal energy,
Okay.
chemical energy, and so on.
Okay, so different buckets
Yeah,
for the different types of energy.
different types.
But then how does it move between those?
Exactly.
We can't just like teleport it
Right.
from the motion bucket to the thermal bucket.
That's where the transfers come in.
Oh,
We define the specific ways
Okay.
energy moves between these stores. So
Okay.
like if a ball is falling,
mm-hmm.
the transfer is happening through the force of gravity,
Okay.
and we can track that energy,
Okay.
moving from the gravitational potential energy store
Uh-huh.
to the kinetic energy store.
I see. So instead of saying that
Yeah,
potential energy is converted to kinetic energy,
right.
we're saying energy is transferred from the potential energy store to
Exactly.
the kinetic energy store through gravity.
Yes.
It's a mouthful,
It is a mouthful, but
but it's more precise.
precisely. And that's key, the language we use
It's important.
when we teach, science is crucial.
Right.
If we're sloppy, we just reinforce those misconceptions.
Yeah.
Like, instead of saying the ball lost energy, if
Right.
energy was conserved, where did it go?
Right. It just vanished.
It just vanished like magic.
So instead we can say energy was transferred from the ball's kinetic energy store
Oh, okay.
to the thermal energy store.
Of the surrounding air through friction.
Okay, so we're saying where it went
We're highlighting the mechanism, the pathway.
and how it got there.
Exactly.
Okay.
And that's what we want to do.
So I'm starting to see how this approach really does help.
Yeah.
It's like we're accounting for every penny in the energy budget.
Yeah.
Nothing's magically disappearing.
Exactly. And by focusing on those stores
Yeah.
and the transfers,
Right.
we're emphasizing that energy's constantly changing and moving,
Yes.
not just appearing and disappearing.
Not just poofing in and out.
Yeah, and it encourages a more systematic way of thinking,
Mm-hmm.
which is crucial, especially when things get more complex.
Okay, let's take a simple circuit.
Okay?
In the old way,
Mm-hmm.
we might say the chemical energy in the battery
Yeah,
is converted to light and heat in the bulb.
right.
But in this new way, how would we frame that?
Well, we'd start by identifying the stores involved.
Okay.
So we've got chemical energy stored in the battery. We've got electrical energy flowing through the wires,
Yeah.
and then light and heat energy emanating from the bulb.
Got it. Okay, so I can visualize all those.
Okay.
But now how do we talk about how it moves between those?
We described the transfer mechanisms.
Okay.
So the chemical energy
Yeah.
is transferred to the electrical energy store
Mm-hmm.
via chemical reactions in the
Sure.
battery.
Yeah.
This electrical energy is then transferred to the light and heat stores in the bulb through the process of electrical work.
Oh.
You see how we're emphasizing those pathways?
Yeah, so it's not just like
Yeah.
it magically happens.
It's not magic. There's a process, a mechanism driving that transfer.
There's a process.
Yeah,
So we're being specific about it
exactly.
to avoid that kind of energy just appearing and disappearing.
Yes.
This is like a detective story,
I like that.
following the trail of energy.
Following the trail.
You know,
was-
we're figuring out the whole story of it.
Yeah. It's about understanding the full story of the energy,
Yes.
not just the beginning and the end.
Not just the start and the finish.
Right, and that's where this energy stores and transfers approach really shines.
Yeah.
Especially when it comes to tackling those tricky concepts like energy dissipation.
Let's talk about that.
Yeah.
But maybe after a quick break.
Yeah, that sounds good. So energy dissipation,
Yeah.
one of those concepts that can really trip students up.
It is.
It's this idea that even though energy is conserved,
Mm-hmm.
it can become less useful.
Less useful,
As
yes.
it spreads out, becomes harder to harness.
Right.
But the energy stores and transfers framework
Okay.
gives us a really elegant way
Oh, okay.
to explain it.
I mean, it's almost counterintuitive,
Oh,
right?
this is.
Like, if energy can't be created or destroyed,
Mm-hmm.
why can't we just keep recycling it?
Right.
Like, why do we even need new energy sources?
Because while the amount of energy stays the same,
Yeah.
the quality.
Could change.
Think of it like this.
Okay.
You've got a perfectly organized toolbox.
Okay.
All your tools are neatly arranged.
I like that.
That's like high quality energy.
Okay.
Easy to use.
Easy to use, right?
Now imagine
Yeah.
someone just dumps everything out.
Oh, no.
Tools are scattered everywhere.
Right.
Same tools,
Right.
same amount,
Yeah.
but way less useful.
Way less useful, right?
Yeah.
Okay, so the energy is still there, but it's more chaotic, less concentrated.
Exactly.
So how does this energy stores and transfers approach?
Yeah.
Help us understand that.
It forces us to account
Okay.
for those leaky transfers
Right.
where energy spreads out,
Yeah.
becomes harder to recapture.
Okay.
Like friction
Right.
in the old energy forms model.
Mm-hmm.
We might just say some energy is lost to friction.
Right.
But where did it go?
Yeah.
It vanished.
Yeah. It felt like a cheat code
Exactly.
in the physics equation.
Exactly.
Like it just skipped a step.
Right. With the stores and transfers model, we have to be specific.
Okay.
So let's say we're talking about
Right.
a block
Mm-hmm.
sliding across a table.
Okay.
We can't just say energy is lost.
Right.
We have to say kinetic energy from the block's motion
Uh-huh.
is transferred to the thermal energy store of the block and the table due
Oh.
to friction.
So we're being specific about where it went.
We're literally picturing the energy flowing from one store to
Mhm.
another.
Right.
And in this case, it's spreading out,
Yeah.
increasing the random motion of molecules,
Okay.
making things warmer.
Right. So we're not just saying energy is lost.
Yeah.
We're saying this much energy went here because of this.
Exactly.
Yeah.
It's way more accountable.
Yeah. It's like we're balancing the books.
Precisely.
Like we can't just, erase a line.
And that shift in thinking is huge.
Okay.
It helps us see why perpetual motion machines are impossible.
Oh, okay.
There's always going to be
Yeah.
some energy dissipating.
Yeah.
Some leakage into those less useful forms.
Less useful forms. Okay.
Yeah.
So let's go back to that circuit.
Okay.
How does energy dissipation play out there?
You're on the right track.
Okay.
We tend to focus on the bulb
Mm-hmm.
because that's where the desired energy transformation
Yeah,
is happening.
That's what we wanted to do.
Electrical to light.
Right.
But even the wires themselves have resistance.
Oh, okay.
So as that electrical energy flows,
yeah.
some of it is transferred to the thermal energy store of the wires.
So that's why they get hot.
That's why they get warm.
Okay. So even in a simple circuit,
Yeah.
we have multiple energy transfers happening.
Right.
Some intended, some not.
Yeah. And those unintended transfers,
That's where our energy efficiency efforts come in.
absolutely. The energy stores and transfers approach
Right.
gives us a framework for
Right.
analyzing
Yeah.
and optimizing.
Optimizing those flows, right?
Like engineers
Yeah.
designing a power grid
Mm-hmm.
can use Sankey diagrams.
Oh, yeah.
You remember those?
Yeah.
From our sources?
Those diagrams with the arrows.
It's showing the proportion.
Showing how much.
Yeah, the flow.
Exactly. Those diagrams become super powerful when you're using the stores and transfers model.
Okay.
You can visually see how much energy is going, where identify those leaky points.
Okay.
And come up with strategies to minimize those losses.
So understanding energy dissipation isn't just knowing it happens.
Yeah.
It's knowing where and how so we can fix it.
That's the key takeaway here.
Okay.
And it goes beyond big engineering projects.
Oh, really?
Even in our everyday lives.
Okay.
This way of thinking can be incredibly powerful.
Okay, like what?
Like if you're trying to keep your house warm in the winter,
Okay, yeah.
you're essentially trying to manage those thermal energy transfers.
So insulation is all about slowing down that heat escaping.
Slowing down that heat transfer from inside to outside.
And suddenly all those tips about, like, draft proofing and double glazed windows, it makes more sense.
You're thinking about those pathways, those mechanisms of transfer.
Right.
It's not just about conserving energy. It's about strategically directing that energy where you want it to go.
Could go.
And this is where I think the energy stores and transfers approach has huge implications, not just for science education, but for how we approach energy as a society.
Like knowledge is power, but in this case, knowledge about energy is power over our energy.
That's a good way to put it.
Yeah, it's like that whole thing, knowledge is power.
Exactly.
But in this case, it's like knowledge of energy is power over how we use it.
Yeah, and it's not just about like what we each do, you know?
Right.
It's like the bigger conversations.
The big picture.
About how we get our energy, about sustainability, about the climate changing.
Yeah.
If we're stuck in that old energy forms and conversion mindset, it's so hard to even have those conversations.
Because the energy is just magically appearing and disappearing.
Exactly. It makes no sense.
Like, how do you even talk about that?
It'd be like trying to plan a road trip without a map.
Without knowing how your car works.
Or like how your car even works. Exactly.
Yeah, exactly.
So this shift in how we even talk about it is so important when we talk about energy stores and transfers.
Yeah.
We're acknowledging those pathways, those limitations.
Okay.
It's not about making more energy.
Okay.
It's about understanding where it comes from.
Right.
How it's stored, how it moves, and like what we lose along the way.
What are those inevitable losses?
Yes, exactly. It's a whole different way of thinking about energy.
It really is. It's like looking at the whole system.
It is a whole system. And then we can ask better questions.
Right. Like when we talk about renewables.
Yeah.
It's not just like clean versus dirty.
Right.
We got to understand like the whole life cycle.
The whole picture. Yeah.
Like how much energy does it take to make a solar panel?
Exactly.
What do we do when the sun's not shining?
Exactly. Those are all about how we store energy and move it around.
So it's not as simple as renewables are good, fossil fuels are bad.
It's way more nuanced than that.
It's about making smarter choices.
Yes.
Understanding what we're giving up, optimizing all those flows.
Precisely. And this is like way beyond just a science class.
Right.
If we can start thinking about energy in this like deeper way, it changes everything.
Totally.
How we build our cities, what we buy.
It's empowering.
It is.
This whole approach.
It really is.
It gives us a way to understand not just like the physics of energy, but our relationship with energy as a whole society.
It's like we got this new amazing way to see the world.
Yeah.
And once you see it,
you can't unsee it.
You can't go back. Energy is literally everywhere. And the more we understand how it moves around, the better we are at dealing with the challenges and opportunities
of today.
Exactly, of the 21st century.
So as we wrap up this deep dive, what's the one thing you want to leave our listeners with?
Don't be afraid to like question those old ideas about energy.
Right.
Like dig deeper. Ask how and why.
How and why,
Think about those pathways, how it's moving, those losses that happen.
Right.
And remember that energy isn't just some like science thing. It's the very heart of like everything.
Well said.
Thank you.
And for those of you who want to keep learning, we've got links to all the resources we talked about, the BEST project, the Singapore-Cambridge syllabus, and those Sankey diagram examples in the show notes.
Awesome.
Keep those energy brains buzzing.
Yes.
And thanks for joining us on this electrifying deep dive.
Thanks, everyone.